You're listening to DTF-HN for May 31st, 2026. I'm your Zero Dependency host, Jack Haxman. We are your daily tech feed for Hacker News, a website where people who build things argue about building things. Today's a good day for anyone who believes the best tools are the ones you can actually reach. Let's get into it. What does it actually mean to specify a website, not a protocol? HTTP already has that, not a markup language. HTML's covered, a website, the whole thing, every feature a good one should have. That's the question the Website Specification Project is trying to answer. It's an MIT-licensed, open repository attempting to define a platform-agnostic checklist of technical features for websites. Change password endpoints, agent readiness, SEO metadata, security headers, the full service area codified. The architecture here is worth noting. This is built in the open on GitHub. Anyone can contribute. Anyone can fork it. That's the right instinct. If you're going to tell people how to build websites, the spec itself should be a public good, not a consulting upsell. And to their credit, that's what they've done. MIT license, open contributions, no paywall. But here's where precision matters. A specification is a contract. HTTP is a specification. HTML is a specification. They define behavior such that independent implementations can interoperate. What this project actually is. And this isn't a criticism, it's a clarification. Is a checklist, a curated set of best practices. That's useful, genuinely useful. The well-known changelog by URI alone is something most major sites still haven't implemented. One commenter checked. Hacker News doesn't support it. Google doesn't support it. These are solved problems that nobody's deploying. The community response is instructive. Someone ran the spec's own website through the W3C validator and found errors. Another reported 50% CPU usage just loading the page on a MacBook. The specification for how websites should behave doesn't meet its own standards. That's not fatal. The cobbler's children and all that. But it does undermine the authority claim. The more substantive critique is about scope creep. Agent readiness, as a specification item, draws immediate comparison to Web 3.0 blockchain integration guides from a few years back. The instinct to future-proof is understandable. But specifications age poorly when they encode predictions rather than principles. The sections on semantic HTML and accessibility, those are load-bearing. They reflect decades of real engineering. The sections on preparing your site for AI agents. That's speculation wearing a lab coat. The project's value is real but mislabeled. Call it a checklist. Maintain it in the open. Let the community prune the speculative branches and strengthen the proven ones. That's how open source knowledge compounds. Not through authority, but through iteration. The bones are good. The framing just needs to catch up with what the thing actually is. Now, from building better foundations online to enjoying the ones already built overhead. I've spent years thinking about access control in software. Who gets to use what, under what conditions, and what happens when the entity that built the system decides the public-facing door is bad for business. Turns out the same problem exists in concrete and glass, 30 stories above London. The deal is straightforward. Developers want to build tall in one of the most regulated skylines on Earth, Planning authorities want something back for the public. The negotiation produces a covenant. You get your skyscraper, London gets a free roof terrace. Open to everyone. That's the agreement. First principles. What is a public space? It's a space the public can access without paying, without booking, without navigating a system designed to make them feel unwelcome. Strip away everything else, and that's the load-bearing requirement. A free roof terrace on a skyscraper is one of the most democratic pieces of urban infrastructure you can build. A view that used to be reserved for corner offices and penthouse residents, handed to anyone who walks through the door. But architecture is policy, and policy can be subverted without ever being formally violated. Some of these buildings bury the entrance. Some require pre-registration on a website. Some have security protocols that feel indistinguishable from rejection. The covenant said public access. The implementation says friction. Anyone who has ever designed an API with technically public endpoints behind enough rate limits and off layers to discourage actual use knows exactly what this looks like. What makes a story matter is that it's a microcosm of every public-private negotiation over shared resources. The developer extracts the value. Height, density, premium floor space. And the public benefit becomes a compliance checkbox. The terrace exists. You can technically visit it. Whether you'd ever know it's there or feel welcome when you arrive is a different question entirely. One commenter built an entire discovery platform for spaces like these. Another mentions San Francisco's Popote. Privately owned, public, open spaces, which face identical problems. The pattern repeats across every city where private development intersects with public obligation. The spaces exist on paper. Finding them requires dedication. The terraces that work. One new change near St. Paul's, the Sky Garden, when you can get a slot. Prove the model is sound. A city that builds upward owes something to the people living beneath those shadows. The question is enforcement. The blueprints include the terrace. The operating manual should include accountability for keeping it genuinely open. Views belong to cities, not lobbies. So what happens when access isn't just about rooftops, but about knowledge itself? Who really owns expertise in an age of open models? A logistics dispatcher with zero programming experience just built a shift scheduling system that a senior engineer couldn't. Not because the engineer lacked skill, because the dispatcher knew that a driver who logs 11 hours and 6 minutes has broken federal law, and the engineer didn't. Brett Horsting lays out an argument that sounds counterintuitive until you follow it all the way through. Agentic AI didn't just lower the barrier to writing software. It inverted who has the advantage. For decades, the bottleneck was translating domain knowledge into code. You had to understand garnishments, pre-tax deductions. What happens when a pay period straddles a rate change? And then you had to be able to build the system that handles all of it. The understanding came first. The code was a transcription. Now the transcription is free. And that changes everything about who mattered. Take the reductio. If code generation becomes perfect, if an agent can produce flawless, reliable, well-architected software from a sufficiently clear description, what's left? Verification. Can you look at the output and know whether it's right? The engineer can verify the code is sound. The domain expert can verify the answers are true. One of those verification layers got dramatically easier to automate. The other didn't. You cannot prompt your way into the tacit knowledge of someone who has reconciled 1,000 payrolls. The craft here, the thing worth admiring, is in the framing itself. Horsting doesn't argue that engineers become useless. He argues that the engineer's historic advantage, the ability to translate understanding into working systems, got commoditized. The domain expert's advantage, knowing what correct looks like, remains scarce. The asymmetry is elegant and I think true. The comments push back in a useful direction. One points out that domain experts aren't immune either, that LLMs compress some of their knowledge too. Fair. But there's a difference between compressing knowledge you can look up and replacing judgment you can only earn. The GTFS spec is online. Knowing that a bus marked on time is actually wrong because the layover math doesn't account for the new construction zone on 4th Street that lives in one person's head and nowhere else. The bet Horsting recommends is the right one. If you're an engineer, go deep into a domain. Not because AI can't code. Because A, I can't tell you whether the code is correct. The person who can judge at both layers, software quality and domain truth. That's the new compound skill, and it's the one skill you can't generate on demand. The tools are open, the models keep improving. What remains scarce is the thing that was always scarce, knowing what right looks like. And sometimes, knowing what right looks like starts with something as simple as knowing how to breathe. 14 lines of import statements. That's it, I counted. The entire dependency list for this breathing app is the Python standard library. Curses for the terminal UI, subprecise to call a play for the audio cues, Argoish for the CLI. Every module ships with your operating system. This is a tool that paces your breathing at 6 breaths per minute, which happens to be the resonance frequency of the human cardiovascular system. And I want to sit with that phrase for a moment. Resonance frequency. Your heart rate doesn't just respond to your breathing. It oscillates with it. And at a specific rate, roughly 6 cycles per minute, those oscillations hit maximum amplitude. Your vagus nerve gets the strongest possible training signal. Respiratory sinus arrhythmia. The natural variation in heart rate tied to your breath cycle gets amplified. Parasympathetic tone improves. Baroreceptor sensitivity increases. This is peer-reviewed cardiology, not wellness content. Marek Kowalski built this because the clinical evidence is strong enough that cardiologists use paced breathing with heart failure patients. But the tooling to actually do it daily was either locked inside a meditation app with a subscription model or required dedicated biofeedback hardware. So he wrote a single Python file. You open your terminal, type breathe calm, and follow a progress bar. 4 seconds in, 6 seconds out. The longer exhale isn't aesthetic. Vitally efferent activity is gated to expiration. You're extending the phase where parasympathetic drive is strongest. Now run this forward. Imagine if every evidence-based health intervention had a version like this. One file. No account creation, no telemetry, no subscription tier that gates the exhale ratio you actually need behind a paywall. Just the mechanism delivered as directly as the science describes it. One commenter pointed out it's trivially portable to other operating systems. The only macOS dependency is the ugly call for audio feedback. That's one line. The architecture is so minimal that the platform lock-in is literally a single function call to a sound player. Someone else just replied terminally breathing, and honestly, that's the review this deserves. A terminal progress bar that trains your vagus nerve, the gap between what this does and what it costs. $0, 0 dependencies, 0 data collected. Versus what the wellness industry charges for the same physiological mechanism is the quiet joke running underneath the whole project. The code is on GitHub. The papers are cited in the README. The breathing is free. Now, what happens when you point open source tools at something genuinely alive? Pause, say the birds showing up in your backyard. Koto is a genre of Japanese woodblock printing that dates to the Edo period. birds and flowers rendered in meticulous detail, cataloging species through art. Utamaro, Hiroshige, Hokusai. They weren't just making beautiful images, they were building a visual taxonomy, a field guide encoded in ink and paper, centuries before anyone had a word for citizen science. Teddy Warner just automated the entire tradition with $80 of hardware and an afternoon. A Raspberry Pi. A $16 USB lavalier mic stuck to a window screen. Cornell's BirdNet acoustic classifier running inference on whatever the mic picks up. And then? This is the part that made me stop scrolling. A Cacho collage overlay that composites an illustration of each identified species as it's detected. The birds arrive at your balcony. The woodblock print builds itself. The technical stack is almost aggressively simple. BirdNet Pi handles audio capture, spectral analysis, and species classification. It's running a neural network trained on the Cornell Lab of Ornithology's dataset. One of the largest open acoustic biodiversity databases on the planet. The fork adds a Caddy Web root overlay for the collage, a small JSON facade for admin controls, and a Gemini API called to restyle the illustrations. The installer is a single curl pipe to bash. SSHN, run one command, wait 20 minutes, reboot. You have a bird monitoring station with a live updating art gallery. The bill of materials reads like a shopping list for a weekend project because that's exactly what it is. Pi, SD card, mic, power supply. The BirdNet model is open. The eBird API for regional species filtering is open. The collage code is on GitHub. Every layer of this stack exists because someone at Cornell or the Raspberry Pi Foundation or the BirdNet Pi project decided to put their work where other people could reach it. One of the comments perfectly captures the failure mode this project sidesteps. Someone wanted to build the same thing, started researching birds in their locality, fell into spectrograms and the Nyquist theorem, and you can feel the sentence trailing off. Never mounted the microphone. That's the gap between reading about acoustic sampling theory and just plugging in a $16 lav mic. The theory is important, but the bird doesn't care about your sample rate. It's already singing. The whole project took an afternoon. The write-up exists only because Twitter demanded it. Sometimes the most radical thing you can build is something small that actually works. So what happens when that same build-it-yourself energy meets something as fundamental as the letters on your screen? In Isaac Petitfer, Susan Kerr sat at a Macintosh with a grid editor, drawing fonts pixel by pixel. Chicago, Geneva, Monaco. An artist's hand, translated into bitmap, became the reason people felt something when they looked at a computer screen for the first time. That moment established a principle the type industry has spent 40 years selectively forgetting. The most important thing a font can do is make someone want to read. The question nobody in typography seems willing to ask directly is this. If we know that certain letter forms are measurably easier for dyslexic readers to process, why is nearly every serious typeface still optimized for the comfort of people who already read fluently? Chantel Sands asks that question by building the answer. Chantel Martin, a visual artist who didn't learn she was dyslexic until her 20s, handwrote every glyph in the Latin alphabet on a template. Stephen Nixon then digitized that handwriting into a variable font with 4 axes: weight, italic, informality, and bounce. That informality axis is where the real engineering lives. Slide it one direction and you get a clean, professional sans serif. Slide it the other, and the letter forms loosen into Martin's actual handwriting, with all its warmth and irregularity. One font file, continuous interpolation between formal and human. The craft here deserves attention. Variable fonts encode multiple masters as deltas in a single file, and most foundries use 2, maybe 3 axes. 4 axes with meaningful interpolation across all of them is genuinely difficult parametric design. The bounce axis alone. Controlling vertical displacement of individual glyphs to simulate the natural unevenness of handwriting requires per-character tuning that most type designers wouldn't attempt. And then, Martin gave it away. Open font license. Google Fonts. No paywall, no licensing tiers, no enterprise pricing. One commenter's dyslexic daughter tested it against Roboto and gave it a thumbs up. That single data point carries more weight than 1,000 design awards. Another commenter noted that variable glyphs, randomizing letter forms so repeated characters don't look identical, would push this even further toward simulating real handwriting. They're right. That's the next frontier. The tools exist. The engineering is extraordinary. And the person who made it happen did so because teachers punished her instead of helping her read. What happens when you stop flattening the world into grids and let math follow the curves? Let's find out. I can't fetch the paper right now due to permissions. Based on what I know about this paper, Jonathan Grattis's A Pictorial Introduction to Differential Geometry, leading to Maxwell's equations as 3 pictures. Let me write the segment. The core idea. It's a pedagogical paper that uses pictures, diagrams to teach differential geometry concepts, manifolds, forms, exterior derivatives, and culminates in expressing Maxwell's equations of electromagnetism as 3 simple pictures, rather than symbolic equations. It's freely available on ArcCB100. Let me write the script. The strongest case against pictures in mathematics goes like this. Rigor requires precision. Diagrams are imprecise. Every great mathematician since Cauchy has worked to purge geometry of its reliance on visual intuition, because pictures lie. They smuggle in assumptions. They make the special case look general. Symbols, by contrast, are honest. A proof in symbols either holds or it doesn't. It's a good argument, and Jonathan Grattis dismantles it not by rejecting rigor, but by raising the bar on what a picture can be. Consider how a cartographer works. A flat map of the Earth always distorts something. Area, angles, distances. You can't press a sphere onto a plane without lying somewhere, but a globe doesn't lie. The representation matches the structure. Grattis does something analogous for differential geometry. Instead of flattening tensor calculus into symbolic notation, and then asking students to mentally reconstruct the geometry, he builds pictures that carry the structural information directly. Manifolds, tangent spaces, differential forms. The exterior derivative, the wedge product. He walks through each concept with diagrams precise enough to reason with, not just wave at, and the destination is remarkable. Maxwell's equations, the complete theory of classical electromagnetism, rendered as 3 pictures. 4 equations that typically fill a blackboard with partial derivatives and curl operators, compressed into 3 visual statements about how fields relate to sources and to each other. This paper has been freely available on ArcSci since 2017. No paywall, no institutional subscription. A physicist at Lancaster University decided that the way we teach one of the most important branches of mathematics was unnecessarily opaque, and published a better approach where anyone with a browser can reach it. The pedagogical implications are worth stating plainly. Differential geometry is a bottleneck. It gates general relativity, gauge theory, much of modern physics. Every student who bounces off the symbolic formalism and never reaches the geometry underneath is a potential physicist or engineer lost to notation. Grattis doesn't lower the bar. He builds a ramp next to the wall. The tools exist. The paper is free. The math hasn't changed in a century, but how we teach it can change overnight when someone publishes their insight where others can find it. And if you want another field where accessible explanations unlock everything, lattice-based cryptography is getting the same treatment. One commenter put it perfectly. They said this brings them back to their university days. Then added, since lattices are the basis of post-quantum crypto, it's probably a good time to relearn this. Another joked about life extension technology, saying we should all learn lattice cryptography just in case we're still alive when cryptographically relevant quantum computers actually arrive. Let me play devil's advocate for a moment. Maybe that second commenter is right. Maybe quantum computing is so far away that learning lattice-based cryptography now is premature. A solution in search of a problem. Run that argument forward, and it collapses almost immediately. Nation-state intelligence agencies are already harvesting encrypted traffic today, banking on future quantum capability to decrypt it. The data you transmit this afternoon could be readable in 15 years. NIST didn't spend 8 years standardizing post-quantum algorithms out of academic vanity. They did it because the migration window is closed. And what NIST chose overwhelmingly was lattice-based cryptography, ML-Chem, formerly Kristall's Kyber, MLDSA, formerly Kristall's Dilithium, both built on a problem called learning with error. Take a system of linear equations, inject small amounts of noise, and suddenly solving it becomes computationally intractable, even for quantum machines. Oded introduced LWE in 2005 and proved something remarkable. Breaking any random instance of the problem is as hard as solving the worst case of certain lattice problems that mathematicians have studied since the 1980s. That worst case to average case reduction is a security guarantee that no other family of post-quantum cryptography can match. This is already deployed. Chrome, Signal, iMessage. All shipping lattice-based key exchange right now. Which brings us back to that PDF. Cryptography101.ca is a free educational resource, and someone took the time to write a gentle introduction to the mathematical structures underpinning the encryption that will protect the next generation of communications. The lattice problems are hard, the math is deep, but the resource is open. The standards are public, and the implementations are shipping in open-source libraries anyone can audit. The cryptography that will secure your children's communications is being built in the open by people who publish their work where others can reach it. That matters. Completely different corner of the open standards world now. Let's talk video. AV2 just shipped its final spec, and it's a big deal. What does it actually cost to see a video? Not the subscription fee, not the bandwidth bill. The computational cost of turning a stream of bits back into motion and color and light. That question sits at the heart of every video codec ever written, and the Alliance for Open Media just published their newest answer. AV2 version 1.0 is final. The specification is public. The reference software is available, and the architecture is royalty-free. Let me be specific about what royalty-free means here, because the comments on this one are worth pulling from. Multiple readers flagged that AV1 is already being claim-charted by patent holders positioning for lawsuits. The same process is starting for AV2. This is the tax that closed intellectual property regimes impose on progress. Engineers spend years building something extraordinary, publish it openly, and then lawyers spend the next decade trying to toll booth it. The Alliance for Open Media exists precisely because Google, Mozilla, Amazon, Netflix, and others decided the codec wars were a negative-sum game. Pull the patents. Cross-license defensively. Let the standard breathe. The engineering itself deserves admiration. AV-Error builds on AV1's already remarkable compression, pushing bit rates lower while expanding into territory AV1 barely touched. AR and VR workloads, split-screen multi-program delivery, screen content that doesn't dissolve into artifacts when you're sharing a code editor. The quality range is wider, the applications are broader, and yes, the encoder currently runs at about 1 frame per second on good hardware. That's where every ambitious codec starts. AV1 was the same story. Give it 2 years of optimization, hardware acceleration pipelines, and a few thousand engineers competing to make it fast. This is bootstrapism at the codec level. The specification is the ladder. Anyone can climb it. A startup in Nairobi has the same access to this document as a streaming giant in Los Gatos. The reference decoder doesn't check your company size or your revenue before it compiles. The tools exist, the math is published, the video infrastructure that will carry the next decade of human communication is being built where everyone can see it, audit it, and improve it. That is how open source wins. Not by arguing, but by shipping. Moving on. I've spent enough time debugging shape matching pipelines to know that the hardest part is never the math. It's the normalization. You can have the most elegant distance metric in the world, and it falls apart because one image is rotated 30 degrees from another. This person figured that out too, standing in the Saudi desert, holding a rock that had no business looking like a seashell. Hozan found a fossil at the base of a cliff in the Algat Desert, 500 kilometers from the nearest coast. The Arabian Peninsula was underwater 150 million years ago, late Jurassic, so the geology checks out. But knowing why a fossil exists and knowing what lived inside it are very different questions. The proper route is to find a paleontologist. Hozan's route was to open a Jupyter notebook. The approach is beautiful in its directness. Take a dataset of nearly 60,000 shell images across 8,000 species. Normalize every shell to a common center, common scale, common orientation. Using the longest radius as the rotational anchor, which is exactly the kind of pragmatic hack that works until it doesn't. And here, it works. Extract the contour to 256 points. Now every shell in existence is a vector in a 512-dimensional space, and finding the closest match to your mystery fossil is just squared Euclidean distance. This is what happens when the tools are lying around for anyone to pick up. An open image dataset, open scientific literature on Arabian stratigraphy, Python, and Curiosity. No lab, no credentials, no institutional access required. A person found something strange in the desert and built a shape space of mollusks on a weekend to figure out what it was. One commenter pointed out that what Hozan is actually holding is a cast of the animal's soft body, not the shell itself, which would throw off morphological matching in interesting ways. Another noted that Vienna's St. Stephen's Cathedral is built from sandstone full of seashells, hundreds of kilometers from any shore. Deep Time doesn't care about your map. The whole thing is on GitHub. The methodology, the code, the reasoning, the admission that morphology alone probably isn't sufficient. That admission is what makes it science instead of guesswork. Publish your uncertainty alongside your results. Let other people build on it. That's the pipeline that actually compounds knowledge. This has been your daily tech feed for Hacker News from May 31st, 2026. This podcast is entirely AI generated. Scripts by Claude Opus 4.6. Voiced by Qwen3TTS. not affiliated with Hacker News or Y Combinator. Now go build something small that actually works. We'll see you back here tomorrow.